So, hi, Dr. Chetna, can we start the meeting now?
Sure, sir. Very good morning to one and all present here, and thank you for joining us at the 3-day International Virtual Conference. Let's start it with the saying of Louis Pasteur: science knows no country because knowledge belongs to humanity and is the torch which illuminates the world. With the onset of pandemic, we came to know a new learning, lockdowns, quarantine, mandatory wearing of face masks, and social distancing. It's true that pandemic has created havoc in everybody's life, but there is a silver lining too. As the pandemic seems to have changed our lifestyle for good, the digital transformation trends around the globe. Video conferencing from home and workplace have become the new normal. This pandemic gives us social distancing with virtual connection. I am Chetna Verma, Master of Ceremony for inaugural program of this conference, and I feel privileged to extend my warm welcome to all our guests and participants to this international virtual conference on Nanomaterials and Nanoengineering 2022, organized by APA Nanoforum. This conference aims to bring together like minded individuals from different countries on a single platform to learn, discuss thoughts, to share ideas, create new ideas, and to ignite motivation. So, without any delay, I would like to invite organizing chair Dr. S.P. Singh, Principal Scientist from CSIR NPL, Delhi, for welcome address. Over to you, sir.
Thanks, Chetna. So, good morning, ladies and gentlemen, dear colleagues and participants. It is my privilege to welcome all the distinguished delegates and guests to this international virtual conference on nanomaterials and nanoengineering, APA NanoForum 2022. This conference is being jointly organized by CSIR National Physical Laboratory and Asian Polymer Association. CSIR National Physical Laboratory is a flagship laboratory of Council of Scientific and Industrial Research, which encompasses 38 laboratories throughout India. I'm glad to be part of this grand event as organizing chair and feel delighted to stay among eminent scientists and academicians from different parts of the world in this virtual conference. So the nanotechnology, a highly interdisciplinary area, has its promising applications at every walk of life and is a dynamic research field. In last 2 decades, the innovation in nanotechnology have enormously impacted various research fields such as drug delivery, bioimplants, sensing, therapeutics, polymer technology, hydrogen energy, solar energy, catalysis, optoelectronics, metrology, and many more, and has also impacted our society in a very positive manner. This prestigious conference is very much dedicated to the advances in nanotechnology. It will offer an exciting platform to the researchers from different backgrounds to showcase their results and interaction with eminent scholars. The conference is poised to provide glimpses of nano world to the students and young researchers and broaden their horizons with new paradigms of nanotechnology. So I have a special word of appreciation and heartiest welcome to our chief guest, Dr. Shekhar C. Mande, DGCSIR, for his address to delegates that would stimulate all of us in our passion of scientific research. I offer my warm welcome to Director CSIR NPL, Professor Venugopal, who has been a source of constant encouragement behind the organization of this event. I further extend my heartiest welcome to Professor Bhuvnesh Gupta, President APA, and Professor Paul Weiss, the plenary guest of honor at this event. I also extend my warm welcome to executive members, chairs, co-chairs, secretaries, and student coordinators who are the flag bearers of this conference. The gravity of conference lies in the presence and interactions of eminent plenary and keynote speakers, along with researchers with various interdisciplinary fields. I extend my warm and heartiest welcome to all of them. I, on behalf of organizing committee of ACS Nano Forum 2022, sincerely wish you a very productive conference, one that will provide new scientific insights, introduce everyone with the state-of-the-art development in the area of nanomaterials and nanotechnology, and inspire the fertile mind. We look forward to hearing the exciting talks and fruitful interaction in next 3 days. Thank you. Thank you very much.
Thank you, sir. Now, I would like to invite Honorary Chair, Professor Bhuvnesh Gupta, President APA, from IIT Delhi for APA address. Welcome, sir.
Good morning to everyone. I'm really delighted to have eminent personalities on the dais today. Sharing the dais with them is always honorable, and it's really a very pleasant moment for me. This conference, which is the 3-day event on the subject of nanomaterials and nanoengineering, is being jointly organized by Asian Polymer Association and National Physical Laboratory, New Delhi. I remember when I had first interaction with Dr. Singh about organizing this conference, he was very positive to go ahead with this. And this is where I admire the consent of Dr. Venugopal from NPL. He's the director there, and he was so optimistic that yes, something nice is being carried out and something nice will come out of this event, so we should go for it. So this is something which I really like, and I see that, I mean, Dr. Venugopal knows that the importance of nano is there, and we have to spread the message of nano to the masses all around. This society, APA, actually, this is the society which was started in 2007. And so it's almost 14 years. And since 14 years, we are trying to organize events here and there. In the same series of events, we organized conferences, mostly in collaboration with other societies or other institutions across the Asian countries. Now, the society is very special in its feature. What is there is that society is India-based society, but this has international members. So we have almost 700 members from all across the Asian countries. And out of the 700 members, we have a 40-member executive committee, which has big stalwarts from the polymer world in Asian countries. So this is a beautiful platform where I can see that there's a lot of interest from the international organizations. And in this APA platform, we started collaborating with the Indonesian Polymer Society. So we did conference in Bali. We did another conference with the Nepal Chemical Society in Kathmandu. That was almost 4 years back. We also did a conference in Mauritius, which was a beautiful venue for the delegates. And like that, we have been collaborating, interacting with different other societies also. Like we had a conference in 2009 that was in collaboration with European Polymer Federation. And like that, the process goes on. So what I'm going to say is that this whole event which we have today is of the same concept that we should go ahead, we should join hands together with different people all around, and we should organize these events in such a way that something innovative comes out of it. So in this 3-day conference, I remember that similar conference we had in 2008. That was first meeting of APA. And in this APA, I remember one more thing, that Dr. S.P. Singh was the first member of this society in 2007. So we have started from that scratch. And in the first meeting itself in 2008, the event was organized by us, but the chief guest was Dr. APJ Abdul Kalam. So the status of this conference was known since the very beginning. And till now, I can say that we are doing a wonderful job as far as the international platform is concerned. We have several awards at the international level, which are given to scientists. There is one award, which is called APA Distinguished Award, which is the top award of APA and is given to the well-known scientists across the world. Similarly, we have awards like Young Scientist Awards, Young Researcher Awards. We have awards for our students, especially for our young generation. We want to encourage them, and we have awards for them, oral awards and poster awards. In last few years, we have even financially supported several students to attend the conference. So this is how the society is very much open to ideas and creativities. And I always like that our young generation, especially our young students, should come forward. They should join this platform. They should join this APA as the International Society, and they should contribute to it. So with this, some information to all my youngcomers, I'm really very glad that we have this event. And I'm really hopeful that at the end of these 3 days, at least our young generation will come out with many more knowledgeable things. And I look forward to a very dynamic event together. So thank you, and thank you so much.
Thank you, sir. Thank you for your very kind and informative words. Now, I would like to request Dr. S.P. Singh to introduce conference patron, Dr. Venugopal Achanta, Director, CSIR, NPL Delhi. Please, sir. Over to you, sir. S.P. Singh.
Yeah. Thanks, Chetna, for giving me this opportunity. And it's again a pleasure to introduce Professor Venugopal Achanta, the Director of CSIR National Physical Laboratory. The dynamic leadership of Professor Gopal has strengthened the existing research at NPL and catalyzed various new frontiers of basic and applied sciences with an emphasis on metrology to at par with international standards. So he has been a professor in Department of Condensed Matter Physics and Material Science at Tata Institute of Fundamental Research, Mumbai, and is on loan from there to CSIR NPL as director. He is member of Senate of IISR Behrampur and IIT Delhi. He is a member of Executive Council of Optical Society of India, Vice Chair of IEEE Photonics Mumbai chapter, and member of Program Committee of Association of Asia Pacific Physics Society, Division of Condensed Matter Physics. Professor Gopal is on the editorial board of many journals like Scientific Reports, Frontiers in Physics, Encyclopedia of Applied Physics, and Indian Journal of Pure and Applied Physics, to name a few. He is an honorary fellow of Metrology Society of India and senior member of IEEE. His research interests are in nano and quantum photonics, having more than 130 publications in Journal of Repute. So we would like to listen to Professor Gopal. So Chetna.
Thank you.
Thank you, sir.
Thank you, Dr. S.P. Singh. Yeah.
I would like to invite our conference patron, Dr. Venugopal Achanta, Director, CSIR NPL Delhi, for inaugural address. Welcome, sir.
Thank you. Thank you, Chetna. Professor Paul Weiss, Professor Bhuvnesh Gupta, Dr. S.P. Singh, and all the organizers. I would like to thank for giving me this opportunity to be here. And I would like to thank Asian Polymer Association for giving NPL this privilege to organize this flagship conference. We look forward to having a wonderful conference where we can exchange. So this conference actually reminds me of Kyoto, right? It's a mix of both tradition and modernity, right? So we are we have these micro symposia which are focusing on nanomaterials, nanofabrication, which are of current interest or recent past interest, but we are going into nano drug delivery, nano energy materials, nano biotechnology, hydrogen energy and devices, focusing on the future. And we are also covering herbal nanotherapeutics in this conference. Like, so this is something which the present government is also pushing for traditional knowledge. Like, so if we can bring it at par with the modern scientific techniques and mix them for the benefit of the society. Right. So it's heartening to see that we are covering energy to healthcare to just pure material science in this conference. And when I talk about old and new, I also see that there is equal importance given to promoting young researchers in this conference, so which is really heartening to see. We have really pioneers in the field who are giving invited talks and plenary talks in this conference. But at the same time, like the conference is also giving large importance to the young researchers who will be the flag bearers for the future in this field. Right. So I would really like to congratulate APA and the organizing team for this wonderful conference, for planning it out and pulling it off. Hearing to Professor Bhuvnesh Gupta about about Bali and Kathmandu being the previous locations, this online session seems to be a little I don't know, disappointing, I would say, like, I mean, for lack of words. But I hope like we'll organize this with NPL as the organizer, as the collaborator in near future in India, in one of the wonderful locations we have close to the nature, right? So I really look forward to this conference in physical mode in near future in India. So let's look forward to that, right? So being at NPL, like, I also have to say a few words about NPL. Our DG, Director General CSIR, Dr. Shekhar Mande, has some important engagement and he couldn't come. So we have some time to fill up. So in the inaugural session. So I'll take a little bit of time, few minutes to introduce NPL. National Physical Laboratory in India is the National Metrology Institute. By virtue of it, we are known as the timekeeper of India. We maintain the time standard, not just the time standard. We also maintain all other standards which are needed for quality infrastructure. So our scientists not just set up standards and disseminate them, but also make sure that there is industry connect. Being part of the CSIR, the Council for Scientific and Industrial Research, so our scientists are also actively involved with industrial research, addressing challenging industrial problems, and also doing cutting edge basic research at the same time. Coming to the material science, just not metrology and industrial problems. So material science has conventionally been a big activity with considerable accomplishments at NPL over from 1950s, right? So from facilities point of view, in India, the first liquid helium plant was set up at NPL in 1952. So we had the first crystal puller, the Zekrolsky system in 1960s. So in 1970s, NPL also developed the synthetic diamonds for industrial grade diamonds were developed at NPL. Superconductors over the last 25 years has been really one of the core areas where we have a significant number of people working on it. So high TC tapes, tubes, rods, joints, right? Even superconducting magnets were made for industrial applications. Even for these accelerators and other things, they were all made and at NPL at one point of time. Semiconductors for both basic research as well as optoelectronic devices, gas sensors. Photovoltaics is another core area where almost all generations of photovoltaics have been worked on at NPL, starting with silicon to thin film, organics, solar, and even now like the perovskites. We have the expertise in-house, having made the first silicon ingots within NPL way back in the 70s and 80s, right? So another area where which is relevant to this conference as well, where NPL has an extremely strong presence is in carbon composites, right? So we have shown applications in orthopedic, limbs and these clutches and other things as replacement of stainless steel clutches to fuel tubes for compact nuclear reactors, the carbon paper for fuel cells, nose tip for a missile or a carbon. So this is extremely long list of accomplishments for carbon composites also in NPL. So overall, being a metrology institute, we focus on setting up and disseminating the standards in the country. In addition, being part of the CSIR family, we address challenging industrial problems. And we also work towards basic research in material science and other activity which is very strong. The third activity which is very strong in NPL is the environmental sciences. Right? So whether it be the station at Antarctica or at high altitude Palampur station or in Delhi, so we have these facilities which are run by NPL. So we're happy to be part of this conference because this falls within the material science ambit of NPL. So I really look forward to having a wonderful conference. We have planned and got really pioneers and excellent speakers for this conference. I look forward to participating in the conference in 3 days. Right? So thank you very much, and wish you all a very pleasant, a very productive conference. Thank you.
Thank you very much, sir, for addressing. Our chief guest, Dr. Shekhar Simande, Director General, CSIR, has expressed his inability to address the delegates due to his urgent meeting. We are going to miss his blessings for our delegates in the conference. Now, I would like to request Conference Secretary, Dr. Sunil Kushwaha, a Principal Scientist, CSIR NPL Delhi, to introduce our guest of honor, Dr. Paul S. Weiss. Over to you, Kushwaha sir.
Hello. Yeah, Chetna, have you? Chetna, your.
So we are calling for Kushwaha sir.
Yeah. Okay. Call.
Yeah. Over to you, Kushwaha sir.
Yeah. Good morning. It is my pleasure to introduce our guest of honor, Professor Paul S. Weiss. Professor Weiss holds a US UC Presidential Chair and is a distinguished professor of chemistry and biochemistry, and also from Material Science and Engineering at University of California, Los Angeles. He received his master's and bachelor degree in chemistry from MIT and his PhD degree from University of California at Berkeley in chemistry. He served as the director of the California Nanosystem Institute and holds the Fred Cowley Chair in Nanosystem Science at UCLA from 2009 to 2014. His interdisciplinary research group includes chemists, physicists, biologists, material scientists, mathematicians, electrical and mechanical engineers, computer scientists, even clinicians and physicians scientists. They focus on the ultimate limit of miniaturization of devices, exploring the atomic scale chemical, physical, optical, mechanical, and electronic properties of surfaces, interfaces, and supermolecular assembly. He has published more than 100 high-repute SCI journal papers, hold for over 30 patents, and has given over 750 invited plenary keynotes and other named lectures. He was the senior editor of IEEE Electron Device Letters from Molecule and Organic Electronics. Professor Wise is the founding editor-in-chief of one of the reputed journal, ACS Nano. Under his leadership, ACS Nano has become a very reputed journal in the field of nanoscience and nanotechnology. He won the Association of American Publishers Professional Society Scholarly Publishing Prose Award for 2008, Best New Journal in Science, Technology and Medicine, and ISI Rising Star Award at record 10 times. Professor Wise has many awards and accolades in his hour. A few of them are: he is a Fellow of American Academy of Art and Sciences, Fellow of American Chemical Society, Fellow of American Association for Advancement of Science. He is also Fellow of American Physical Society, American Vacuum Society. He got several awards, like he received IEEE Pioneer Award in Nanotechnology, American Vacuum Society Nanoscience Recognition Award. Also, he received Nano Smart Prize. He is also recipient of National Science Foundation Presidential Young Investigator, and so on. So we are more eager to listen Professor Wise talk. I just thank you.
Thank you, sir.
Wise, yeah. And
Thank you, sir.
over to
Yeah.
you.
I would like to invite our guest of honor, Dr. Polarizability, for the inaugural plenary talk. He will be speaking on atomically precise chemical, physical, electronic, and spin contacts and interfaces. Welcome, you, sir. Over to you, sir.
Well, thank you so much for having me and for this honor. Let's see if that works. How's that? The correct screen up? Great. Okay. Well, I can't take you to Kathmandu or to Kyoto, but I'll bring you to Los Angeles for a little while, where it's already evening, but still very beautiful. And so what I wanted to do was talk about something that was really a dream that we thought of. I'll explain that in a moment. And I'll warn you in advance that I won't have a punchline, but that because of a paper, really a comment that was written about a paper that we had written, we jumped a decade forward in terms of our thinking, in terms of how to make atomically precise contacts. And then I'll give you a glimpse of what we're doing beyond electronic contacts, and that is in our efforts to control spin at interfaces, at molecular interfaces. And so let me take an almost trivial example of why we might want to do this for the extraordinary material graphene, for example, right? The way we make contacts to it now is we evaporate metal on top of it, and we thereby destroy its amazing, mechanical, optical, electronic properties, or we oxidize a little bit, breaking the conjugation, again, destroying the properties, and then we reduce back a little bit to make some chemical interfaces that are not well controlled. And so I argue that instead, we should be able to use more than a century of organic chemistry to make atomically precise connections, predictably, to know where every atom is, and because we're able to visualize those contacts in these 2D materials, and in fact, as I'll show you in others as well, what we can do is get perfect band alignment by design. Make sure there's not a node at the contact, and thereby optimize and make what I would call perfect contacts. And so that's our dream and goal. And there's room for everybody essentially in this audience, in this exercise. And that is the chemists, the physicists, the material scientists, the engineers. And I'll show you along the way how we've studied such contacts and how in certain cases we've been able to obtain already a perfect band alignment by design. And then hopefully you'll see where we're going. And really in my fantasy, you'll join this effort. Okay, so there's a whole cast of characters, working on these projects. I'll try and put everyone's name on every slide as we go along. In a few days, a paper will appear in ACS Nano that is a forward-looking review article on where we think we can go with spin control. And we'll see some of these data as we go along. This work was funded largely by the NSF, the Fulbright Foundation, the Keck Foundation, and the Kavli Foundation. Okay, before I go further, what I would like to do is share with the students and postdocs in the audience the special opportunity they have being trained in nanoscience and nanotechnology. So at the 10th anniversary of the US National Nanotechnology Initiative, we were asked by the White House to say what it is we had done with more than $1 billion per year in funding and what we might do if that funding were to continue. So those seemed like two very important questions to answer. And we realized that the main scientific insight we'd gotten was paradoxically, in conflict, in that we're able to make atomically precise structures and measure their properties. And that's the motivation for much of the talk today. But we also learned that when we measure the same structure over and over and measure its function, we often get a different answer. And when I say the same one, I don't mean the chemically the same one, I mean even the very same assembly. But that's the subject of a different talk. In biology, that's even more important, where function changes contextually and so forth, and there are important aspects of control. The other thing we realized that much like in the biotechnology revolution, the advances in nanoscience and nanotechnology grew and accelerated on the basis of new tools that had been developed to let us explore the nanoscale world. And then we realized one further thing, and that is uniquely in nanoscience and nanotechnology, because the field had developed by bringing in people from chemistry, physics, material science, engineering, medicine, toxicology, data science, and so forth, that we'd learned communication skills that other fields had not. We'd become inclusive, that we asked people in other fields to share their problems and to share their approaches, and we shared ours, and we developed new tools to take on those problems and new approaches working together. And even though, and I'll pick on another field, the one that my wife is a leader and pioneer in, neuroscience. You'd think that to understand the brain, that you would want to include biologists and physicists and chemists and data scientists and engineers and so forth. But in fact, neuroscientists and neuroscience as a field is somewhat exclusive. And so when we developed the BRAIN initiative in the US, which was actually proposed by a team of nanoscientists that I put together, and we also put together the technology roadmap for it, we had to calm the neuroscientists down to get them not to kill it. And so as a trainee, you have, I think, an opportunity and also a responsibility to look at other fields and their problems and to take those on. In my own group and more broadly at UCLA, I lead an effort, and more broadly globally, one of the things we do with clinicians, so the MDs and MD PhDs that I train in my laboratory, when they're going on their rounds in the hospital, one of the things they're doing for us is reconnaissance to look for problems that we could possibly solve. What did this patient need in terms of diagnostics or therapeutics or other opportunities that are out there? And we put this in an editorial written by an interventional radiologist and a bioengineer and me. Okay, so if you're a trainee, I would say look broadly at the field out there and see where your interests lie and where you can contribute. Okay, back to motivation a little bit further now. So once upon a time, I was at IBM and Heine Rohr and Gert Binnig and Christoph Gerber had recently invented the scanning tunneling microscope. Don Eigler and I had been at Bell Laboratories, then moved out to the IBM Almaden lab in California. And coincidentally, both of us had the same favorite rare gas, which was xenon. And in my last 4 days at IBM, before I started my first professorship, we decided we'd look at xenon atoms on a surface. And we found that they were sitting out in the middle of atomically flat terraces, and we couldn't figure out why that was. So one night, we reprogrammed the microscope, and the next day, I spent the day moving atoms around to find out what was underneath them. And that was the original reason for moving atoms. And it turned out wherever the atoms and clusters were sitting out in the middle of the terrace, there was a defect site that was capturing them there. Don later learned to spell IBM, and he made this famous quantum corral image of iron atoms on a copper surface. And one of the things, having been trained as a chemist, as you heard, was that these interference patterns in the electronic structure at a particular electron energy look like enhanced and depleted orbital occupancy. And so if I were an atom or molecule that liked electrons at this energy, or liked orbital density at least, if it was an empty state, then I would go to the middle of this ring where there's no extra atom. There's an extra local density of states there. And these patterns change as a function of energy. And you can do a kind of spectroscopy by decorating these sites, much like people who study superconductivity do to decorate vortices, but we can do it with atoms or molecules. And so that satisfied another aspect of what I was looking for in science, which was to look at how electronic structure and chemistry were coupled. So from that point of view, the most important image ever recorded, it was actually a pair of images with the STM, was this one, where Joe Strosio and Randy Feenstra at the East Coast laboratory of IBM at Yorktown Heights looked at the stoichiometric gallium arsenide 110 surface. And I teach first-year undergraduates who would be happy to hear me say that arsenic is to the right of gallium on the periodic table, so it's more electronegative. And so on this stoichiometric surface, there's charge transfer from the gallium to the arsenic. And so it's as if we can put on goggles and look at the surface with better than atomic resolution as an atom or molecule would see the surface in traversing it. So if there were an electrophile, it would go to the filled states, which are on the arsenic atoms. And if we're a nucleophile, it would go to the empty states on the gallium. Now, it's a little more complicated than that, and we can do spectroscopic imaging to map the energy and spatial distributions of these orbitals. But it gave us a way to look at the surface as a molecule would, and that got me very excited. So now let's fast forward a bit. And remember, I told you about this opportunity to do spectroscopic imaging at the edges of a piece of graphene and then try to make contact to it. And that's part of the motivation, but in fact, it goes to many other materials, as you'll see. So for transitional metal chalcogenides, for instance, the sulfur or selenium typically used can be substituted for a molecule that ultimately could form a contact. That hasn't yet been done. But what Taki Lee at Seoul National University did was he showed that he could fill vacancies at the surface with alkane thiols and thereby pacify the material and improve its electronic properties. So what I'll show you is we know molecules that we can use that control the charge distribution and also conduct that could be bifunctional so as to form a good and robust contact to these materials. These will be a little more complicated because now we don't have complete exposure anymore. And then we'll even go to organic electronic devices and others. And I'll show you that one of the tools we saw that we needed was the ability to peer below the surface at buried interfaces. And so we spent quite some effort and many years developing those capabilities. Now, the way we got into this effort was once upon a time in my laboratory, when this field was just getting started, the IBM laboratories and Bell laboratories pretty much owned all the semiconductor surfaces. And so there was no point in competing with them. We have a rule in the laboratory that if someone else can do an experiment, they can have it. And in academic laboratories, the people who studied metals were mostly interested in catalysis and corrosion. And that wasn't so much where my interests were at the time. And we saw that no one had the ability to get atomic resolution spectroscopic images of insulators. And so we developed a tool that would allow us to dribble electrons back and forth between the tip and sample at frequencies higher than the charge dissipation rate, so up in the microwave frequency range. And we developed that for a number of purposes that we, for the most part, won't be talking about today. But in order to look at as wide a range of samples as possible, we went to my colleague, first at Bell Labs and then at Penn State, Dave Alara, who with Ralph Nuzzo had developed these alkane thiolon gold self-assembled monolayers, which I suspect most of you are familiar with. These form one molecule thick, two-dimensionally ordered layers for the saturated chains on the gold 1-in-1 surface, which is the most common surface studied because it's the low energy compact surface. The molecules tilt over 30 degrees to optimize the van der Waals interactions between the chains. Also, since these are saturated chains, they can kink. And so one finds dynamically gauche defects at room temperature. Typically about 8% of the bonds are kinked, and tilt domain boundaries where different domains have tilts in different directions. And then there are also things like missing molecules, monatomic step edges such as these have molecules that can't line up across them because of the particular positions of the molecules. But at the time we entered this field, the thinking was that these molecules went down randomly and irreversibly on the surface, and were that the surface composition would represent the solution composition, and that the molecules were immobile once they were there. And so even before we turned on the spectroscopic imaging tools, what we had decided to do was differentiate between different molecules using the spectroscopy we developed. We realized just with conventional STM that all those ideas about the surface were incorrect. The surface composition did not reflect the solution composition. These monolayers were dynamic. They phase separated. We could see the domain coalescence over time. And so this really led us to the ability to develop chemical patterning methods on the surface. And George Whitesides and others, really led a lot of this effort at larger scales. And then we led at the smallest scales, where we could isolate individual molecules at a domain boundary, for instance, and we could process the films so as to make a single kind of defect dominate the surface. And one of the hosts of this meeting, Dr. Ajit Kumar, put in a molecule that could be a photo switch into these defects and showed the first measurements of a single molecule photoisomerizing, in analogy to the way you're seeing this slide right now with the photoreceptors in your eye undergoing cis-trans isomerization. So we saw this opportunity to isolate single molecules and pairs of molecules, lines of molecules, and clusters, and we could deterministically get what we wanted on the surface, first by manipulating the defects so as to restrict access from solution, vapor, or contact into the defects to reach the substrate and to attach there. And so one of the early experiments we did was Mark Reed at Yale had shown that if you take 10,000 of these oligophenylene molecules and put them in a small hole that he'd punched in a silicon nitride membrane with metals on either side, that those 10,000 molecules functioned as conductance switches. And so then there was an argument over how the molecules switched and whether a single molecule could switch. And so we isolated individual molecules using the process I just described, and we objectively tested each of the proposed mechanisms by including and excluding the key chemical functionality required for switching. And to our chagrin, we discovered that all 6 proposed mechanisms had to be wrong because we could make the molecule switch whether or not those key components were included. And ultimately, we determined that the switching was the result of motion, of the tilt of the molecules, which changed the hybridization of this buried bond. And you'll notice here that just like in the semiconductor world, the contacts are everything, right? They're simultaneously the chemical, the physical, the electronic, and the mechanical connection. And so that's where this idea of using chemistry to control and to optimize the contacts came in. We then also showed we could drive these molecules from one state to another using an electric field applied by the tip. And we could even redesign the molecules to invert their dipole so that we'd switch their electric field interactions, and it would be as if we rewired a wall switch and drive them in the opposite way. So these experiments left us with 3 sets of questions. The first was, how quickly could they go from one state to another? What's the slew rate? And since it's a frustrated rotation, we concluded that should be in the gigahertz. The second is, what's the conductance of the buried bond? Important for the rest of this talk. And the third question is, what are the absolute structures? We'd gotten some indirect measurements by designing the matrix around them so that they could. Someone needs to mute, I think. So that we could stabilize one state or another with hydrogen bonding with the surrounding matrix. And we could even design the matrix then to control these interactions down to 1/10 of an angstrom, while simultaneously controlling the placement of the molecules out to the centimeter scale. So really, in some ways, what we did is add the chemical dimension to nanolithography on top of these other efforts. And so, for instance, in order to measure the absolute structures, we came up with a way to measure the tilt of individual molecules. So there'd also been an argument about what one measures in these systems with a scanning tunneling microscope. Is it the exposed surface? Is it the buried interface? Is it the integrated tunneling path? And so what a clever postdoc in the laboratory, Patrick Hahn, did was he used a combination of longer and shorter chains that formed identical structures. And then he showed that as long as the tip didn't come into contact with the film, in other words, working at high gap impedance, and we did this experiment in our ultra-stable low temperature microscope to get these quality of data, he was able to show that there was an offset for the shorter chains in the field of view of longer chains. We did many different combinations. But then we realized we could also simultaneously measure the buried interface, because there's a way to measure the largest buried dipole in a system, and that is by modulating the tip sample separation a fraction of an angstrom. And what that does is when you plot the derivative of current with respect to separation, that measures what's called the local barrier height. And since the sulfur gold bond is the largest buried dipole, and all the sulfur gold bonds in a domain are in registry, we get a single lattice, no offsets. And then we figured out how to tell which top goes with which bottom. And we did that by working with the domain boundaries. And so we got the absolute polar and azimuthal tilt angles in this way. And we can apply that more generally. If there's more than one dipole, we can image that as well. So for instance, in these amide-containing alkane thiol molecules, hydrogen bonds can form that double the interaction strength between the chains, which before was just the van der Waals interactions, but the hydrogen bonds add extra strength. And so what we can do is simultaneously image the sulfur gold bonds and these hydrogen bonds. Well, you'll see the data don't jump out at you like the previous ones. And so we had to work with two prominent mathematicians here at UCLA, Andrea Bertozzi. You might know her little sister, Carolyn Bertozzi, the editor-in-chief of ACS Central Science, and then Stan Osher, who won the equivalent of the Nobel Prize for Applied Mathematics. There's the Field Medal for pure math, and then the Gauss Prize for applied math. It's only been awarded 3 times, and Stan had that one. And so working with them, we developed these algorithms that let us pick apart these images and figure out the positions of the molecules and the parts of the molecules. And what we discovered, to our surprise, was these hydrogen bonding networks continue across domain boundaries and even across regions of disorder. So they passivate the surface very well, even if our monolayers lack perfection. And that actually explains some earlier data where we had taken liquid metal nanoparticles that we wanted to use to do inkjet printing of electronic circuits. And if we put just saturated chains on them, when we tried to break them up into little liquid metal nanoparticles, they got oxidized and they just end up being junk. Whereas if we use the amide-containing alkane thiols, we could break them up into a rather monodisperse suspension with very little oxidation. So even where the substrate atoms are moving around, these hydrogen bonds hold, and even when we're bombarding them with ultrasound. It's quite amazing. And so this turns out to be an element-efficient way to produce printable metals. Okay. Going back to the microwaves for a moment, one of the things we can do with them is to measure the polarizability of the molecules attached to surfaces. So as you know, pi electrons are more polarizable than sigma electrons. And so when we go from saturated chains to amide-containing alkene thiols to fully conjugated molecules, the polarizability quantitatively increases. When we go to the switches, we can look at the same molecule in the on versus the off state, and we see that the polarizability is different by a factor of 2. That's because the substrate electrons, when the molecules are in the on state, can contribute to the polarizability by going in and out of that buried bond. And so in this way, we have a way to measure buried contact and to quantify the conductance of that contact. Well, we had looked at this problem from a different perspective earlier, and these were the first measurements of the conductivity of individual molecules. What we did is we used combinations of longer and shorter, in this case, saturated chains. And at the time, it was thought that there might be cooperative effects. And so we made sure to have domains of one molecule, domains of another molecule, and then single inserts of one molecule in the domains of the other, and vice versa. And so we had all the combinations we needed on the surface. We knew we learned to process the films to make that happen. The physical height difference here is 2 angstroms for adding 2 methylene units. And we did many different combinations here. And as you see, under these particular tunneling conditions, the apparent height is 1 angstrom different. And it doesn't matter whether we have isolated molecules or domains, it's the same difference. So on doing that for many combinations, we could figure out, okay, what's the conductance of the chains? What's the change in the current as a function of separation when we're outside of the film? And not coincidentally, we lose resolution of the molecular lattice once the tip penetrates the film, which is this yellow region. And then for our purposes here, what we can do is extrapolate down to 0 chain length and get the contact conductance. And so at the time, there was a controversy over what would make a better contact. And we mistakenly spoke of molecular alligator clips. And that if you told me what contact material you wanted to use, I should be able to tell you what functional group to use. And it turns out to be not so simple. And in particular, people argued over gold surfaces and whether sulfur or selenium would be a better contact. Selenium's a little bit bigger, right? It's just below sulfur in the periodic table, and it forms a stronger bond to gold. It's actually disruptive of the surface in some cases, and there's a stable gold selenide mineral. So we did, again, many different combinations of lengths, but for this one for which I have the schematic here, you can see the selenolates are slightly larger for the same alkyl chain length, but the tip has to be closer. And the apparent tip height or the apparent height in STM images is our proxy for conductance. So since I drew this to scale, you know immediately that the selenolates are less conductive than the thiolates. And we can quantify that and do the many different combinations, the extrapolation down to 0 chain length, and show that for the saturated chains, the thiolates are 5 times more conductive than the selenolates. But there had been calculations that said sulfur was 5 times more conductive than selenium and also 5 times less conductive, and a number of calculations in between. So we went to the literature to find out why some theorists got it right and some got it wrong. And it turned out, what jumped out at us was that nobody necessarily got it wrong. What they were doing is calculating different backbones. And we realized that the key feature here was, what's the band alignment? And so the bad news was, if you tell me a contact material, I can't tell you what the optimal functional group is. But the good news is that by shifting the band alignment, we can optimize the contact conductance. And then other groups studied isonitrile, and other people figured out, also the importance of band alignment in these cases. Okay, so I think that was what I wanted to cover there. Hold on. So let's take a little graphene. Yeah, let's take a little graphene interlude now. So back to Patrick Hahn, who moved from being a postdoc to being a research assistant professor in a lab that we ran in Tohoku University for 10 years. So we got a little bit closer to Kyoto anyway, for those who are missing travel. And his particular interests were in chiral graphene nanoribbons. And we, and in particular he, had studied what's called the Ullmann coupling reaction to connect together aromatic molecules on surfaces previously in the laboratory. And we figured out how those worked and how the precursors to the reactions formed assemblies such that when the, in this case, copper surface broke the carbon halogen bonds, the surface helped zip together the biaromatics and larger polyaromatics. And so people had previously studied the armchair graphene nanoribbons quite extensively and the zigzags. And you might recall that while graphene itself is a semi-metal, there's no band gap when in the semi-infinite case. When you take the armchair graphene nanoribbons, as they get narrower, the band gap increases. And for the zigzag nanoribbons, the edges have interesting spin properties. And we wanted to know what the properties of the chiral graphene nanoribbons are. And again, when we use scanning tunneling microscopy, every sample is monodisperse. And so we're able to look specifically at one and its properties. And so what Patrick did is he predicted the precursor that would form the assembly as a reactant, as reactants that would lead to the graphene nanoribbon that he wanted. And his first design was successful. That's how much we knew about these. And the reason we use the copper surface is as follows. Aromatics sit far off the equivalent gold surface and are not strongly perturbed by it. It turns out under the right conditions, you can make the reaction go on gold or silver. Silver is still pretty much like gold. There's not much perturbation. The aromatics sit far above. We've done a series of experiments where we could peer right through aromatic molecules like benzene on a gold 1-in-1 surface, but the copper interacts strongly and easily breaks the copper halogen bond. And so that's why we use it for these reactions. This reaction's been known for over 100 years and, going back to Ullmann's original paper. Okay, so we were able to, at low temperature, measure the reactant assemblies to raise the temperature to the point at which we broke the carbon halogen bonds that hadn't yet zipped together the aromatics, then raise the temperature again to make the chiral graphene nanoribbons that we predicted. And what Patrick did is he did a bunch of those reactions on the surface and showed that as a function of growth direction going around the clock, one alternated between left and right, left and right, left and right chiral graphene nanoribbons. A former postdoc in the group, Nacho Pascal, now at in San Sebastian, took a vicinal surface, one where terraces are all in the same direction, and showed that in that case, he got a single chirality of these graphene nanoribbons everywhere on the surface. It was a beautiful set of experiments. Okay, and so we're able to do the kind of spectroscopies that I told you about earlier, where we could map the molecular orbitals as a function of energy. One of the nice things for a former optical spectroscopist such as myself is that in order to tune the energy, all we do is dial in a voltage, and that voltage gives us electron energies that are that voltage times the charge on an electron, conveniently measured in electron volts. And we can look at filled states by having electrons tunnel from our sample to our tip, and we can look at empty states by reversing the polarity, like in the Feenstra and Strocio paper, by having electrons go from the tip into the substrate. Okay, so at this point, someone wrote a comment about our paper saying that under different conditions, at higher temperature and higher coverage, they got a different product. And so, that I would say is not unreasonable, but in order to address their comment, what we did is we reproduced their conditions, and they had concluded that our mechanism was incorrect. We were actually able to show with higher resolution images from our microscopes that our mechanism was correct, but they were correct that one makes different products under those different conditions. And when I saw these junctions, what jumped into my head was, hey, we've made contacts to graphene nanoribbons. And so I wanted to explore those contacts. And so it's a longer story to tell you why I have post-traumatic stress disorder about phase relationships, but just let me tell you that. And so not only do we measure topography, but we measure what's called differential conductance to look for nodes. A node in a contact would be very bad, right? That is not how you'd conduct electrons through smoothly. What we want are smooth electron orbitals that don't have nodes in them and are continuous across the contact. So these straight nanoribbons, sure, that's fine, but can you really make a device that's straight forever? And I'll show you a little later. The answer is maybe, but that was not so interesting. This one in topography looked pretty good, but when we measure the phase, we realize there's a node right in the middle, not good, right? All these stripes are bad. These stripes are a nightmare. And so what we need to do is make a number of different precursors, put them together, measure the contacts, and determine the phases and continuity and so forth. We haven't done that yet. So please stay tuned for those experiments. In the meantime, Roman Faisal and really the top person in the world at making these precursors, Klaas Mullen, jumped into the argument and showed that with non-contact AFM, that we got the products we said we did under the conditions we said we did, and that our mechanism was correct. That was nice of them to do that. In the meantime, the Berkeley group did some very clever things. One is they made these inline, quote unquote, devices by changing the width of armchair nanoribbons, right? So they're modulating the band gap inline by doing that. They also made these zigzag structures where with different side group functionalities, they shifted the bands, again, as a way to make kind of diode on the surface. And you can imagine making larger structures and even being able to take turns, that kind of turn, with these ideas. So they've been very creative in this area, and we'll come back to them at the very end of the talk. In the meantime, what I want to do is introduce you to the molecules that we try to use as contacts. So these are carboranes, where every one of these green spheres is a boron atom. The black spheres are carbon. I'm not showing the hydrogen on each atom, but the unusual feature from the point of view of chemistry is that the carbon atoms here have 6 bonds. Because they have 6 bonds, they're electron deficient, So whatever isomer we choose of these, and these two are commercially available, but actually we have access to all of them for reasons we can discuss. Wherever you put the carbon atoms is where the positive charge on the molecule will be. So in addition to that, whatever isomer you use forms identical lattices on the surface because the lattice is only determined by the projection of the cage on the surface. Unlike the saturated chains, they can't kink and they don't tilt. And so just by symmetry, we've eliminated 3.5 out of 4 types of defects. And you can see it's even hard to see the domain boundaries here. There are actually 5. And they are only the result of offsets and registry of attachment that are either translational or rotational. So these are very robust monolayers where we can control their interaction strength and we control the surface charge. Because here, since the carbon atoms are on the side, we end up with a non-polar surface. Here, the carbon atoms are up, we end up with a positively charged surface. If we put the carbon atoms down, we end up with a negatively charged surface. And so we can shift the band alignment using these. And in fact, they're aromatic, unless you ask Roald Hoffman, who says aromatic molecules have to be flat. But despite his Nobel Prize, I think he's wrong. Just my, well, not just me, but anyway. And we can show at the macroscopic scale, the neutral and positive charge, and we can measure that at the nanoscale as well. So we can use that for organic electronics, where what we want to do is get band alignment between our contact and our active layer. And the way that's been done in the past, for instance, what Seth Martyr at Georgia Tech did is he put a polymer interlayer and then added fluorine to tune the negative charge. But if you add fluorine to a polymer, you make Teflon, right? And you change the wetting properties. And so that isn't a good solution from my point of view. And Jay Kim, a postdoc in my group, came up with the idea of using mixtures of carburenes. He did this for both gold and silver, and he was able to shift the bands over about 1 EV and get perfect band alignment by using the right combination while not changing the wetting properties and not changing the morphology of the polymer. So 2 weeks after this paper was published, Intel stole them away and started working on this kind of surface control. We've also been able to do the same thing on germanium surfaces using carburenes and control the surface charge. And the student who led that project, Andrew Serino, went off to Lam Research immediately afterwards and started working on this kind of band alignment for semiconductor materials. Okay, I'm going to finish up with just a little bit of a taste of what we're trying to do in spin. And so Ron Nauman at the Weizmann Institute discovered that when electrons, in his original case, photoelectrons, go through chiral molecular layers, there's spin filtering. And he did that with DNA on surfaces, for instance. My colleague here in electrical engineering, Clarissa Ayo, looks for what kind of quantum effects and spin control may exist in biological systems. So much like in the earlier experiments I showed you, we try and pick these ideas apart in reductionist ways and reproduce phenomena and quantify them and try and understand their origins. And so while there were arguments about whether this effect existed or not, and there were typically, 1 or 2 experiments in a paper, and there'd be a big effect or no effect, I think the experiment that really nailed it was one that Bert Meyer at Eindhoven did with Ron Nauman, where they took the idea that in electrochemical water splitting, that a side product is peroxide. But in order to make peroxide, you need electrons of opposite spins. And so by using chiral monolayers, they were able to turn off the side product, the peroxide, in a demonstration of spin selectivity. And so I think there's a lot to do here in terms of control. In a bigger picture, it fits into a real interest of ours, which is, why does nature choose such poor molecules as conductors, right? We use inorganic metals to move electrons around. We use activated processes in inorganic semiconductors, like in chips on all your computers, to make decisions. I understand why you don't want to have a couple of EV electrons around for activated processes, because those can also break bonds in biology. but then why choose the molecules we do? And why do some of the empirical ideas like Dutton's rule in biochemistry, why does that work as well as it does? Why do electrons go further than we think they should? And we can see, for instance, in carefully protected systems that capture light, like our photoreceptors or in photosynthesis, how that would work. But more generally, we do move charge around in biology. And so, we want to understand that at at the molecular scale. And so spin is one possible means of protection in terms of getting electrons, from one place to another. And so we've set up fluorescence experiments using DNA, where we could have 100,000 parallel experiments and flip the magnetic field of the same substrate and use the spatial encoding to determine how effective the spin filtering was. We've done spin polarized low energy electron microscopy. We've done electrochemistry, and now we're doing scanning tunneling microscopy. A system that we're particularly excited about comes from molecules developed by our collaborator in Prague, Thomas Baza, who's made the first chiral carboranes. And we have both the left and the right-handed ones separated so that, again, we can spatially pattern them on surfaces. We can flip the magnetic field with the substrates that Eric Fullerton at the UCSD Magnet Center makes for us. And then we can measure photoelectrons at the high energy case, lower energy electrons in the tunneling cases. So stay tuned for those experiments. And I'll point out a paper that just came out at the end of last year, where Felix Fischer at Berkeley used some of these nodes and careful control of graphene nanoribbons in order to get topological defects that then control spin. So I think there's an opportunity there where we're proceeding is to build in either dopants or vacancies into these tiles so that we can control the pitch and spacing of them. These are made by Klaus Mühlen. And then if we offset them from the center when we get the various rotations, we can also look at the distance dependence. So I'll stop there and just tell you, hopefully some of you will be interested in joining this, this venture into trying to make a perfect context. I tried to put everyone's name on every slide as I went along. These are the people who paid for this work, especially now the Keck Foundation just gave us a center, DOE and NSF for the instrumentation, as well as NSF for studying the chiral layers. And then we have collaborators around the world. I'm looking forward to getting to India on this distinguished visiting position at IIT Madras. And, as you've seen, we went from developing new tools to understanding the placement of molecules, to isolating them and measuring their function, to patterning them to do side-by-side experiments. And that's led us, hopefully, through all this effort into making something beautiful that we can study and to be able to understand the natural systems which awe us. So I'll stop there. And thank you again for this great honor to be able to talk to you and lead off the conference today. Thank you.
Thank you, sir. It was a great pleasure to have you and listen to your wise words and learn so much from it. We are sure that your message would be vision forward for all our scientists, delegates, and especially for our young generations. So thank you very much, sir. Now, I would like to call upon Conference Secretary, Dr. Sunil Kushwaha, Principal Scientist, CSIR and QS Delhi, to propose vote of thanks. Over to you, sir.
Thank you, Dr. Chetna. So it is my privilege to propose vote of thanks in this inaugural ceremony of International Virtual Conference on Nanomaterials and Nanoengineering on 24 to 26 February 2022. It is our honor that we have distinguished guests joining this conference on this special area of nanosciences. Now, I am highly grateful to our director, CSIR National Physical Laboratory, Professor Venugopal, for his blessings and guidance to our delegates. We wish that your work would help in taking this conference to newer dimensions. We are also thankful for the presence of Asian Polymer Association President Professor Bhunesh Gupta from IIT Delhi for his inspiring directions to delegates. I would like to give thanks to Professor, our guest of honor, Professor Paul White, University of California, USA, for his plenary address, which will bring a new energy in our delegates. And Professor White, has beautifully explained the capability of STM for the polarizability of molecules at nanoscale, as well as contact conductance of single molecules along with atomic scale imaging. And also we talk about the chirality in the graphene as well as in the even chemical organic molecules. Also, we are thankful to our honorary chairs, conference chairs, organizing chairs for their addresses to delegates, which will open a new pathway to the conference organization. We are highly thankful to our delegates and guests from different parts of the world for their participation in this conference. We wish that these events offer a highly interesting platform for our delegates. We express our thanks to our plenary talks, keynote addresses, invited lectures given by highly reputed scientists from different institutions of excellence. Big thanks to our organizing secretaries, student coordinators, and technical committee for their strong support to this event. Our sincere thanks to our sponsor of this conference, which made this event more dynamic in terms of organization. I am highly grateful to CSIR NPL team, CSIR NPL technical team, and APA for this joint activity. I am sure this event is going to be highly informative in terms of science and technology of different nanomaterials, and we look forward to very creative interactions with all the delegates during this 3-day conference. Thank you so much. Now, Dr. Chetna.
Thank you, sir.
I have, sorry, I have one question. Like, so could Professor Weiss, there are quite a few, I mean, it's a wonderful talk, the journey on atomically thin layers. I'm sure quite a few questions will be there. Would you like to take a couple of questions, please?
Of course, I'd be happy to.
Okay. So, I mean, I have one question myself, which is there any way we can control? I mean, you have showed nicely that the hydrogen bonds are the culprits which cause these defects. Is there any way to control these to reduce the defects?
In which systems?
In the gold, on gold, like so what you're showing.
I see. Yeah. So really what the carburenes have done for us is just through symmetry considerations, reduce the defects very dramatically. And in fact, you know, you can block access to the substrate using them, which in many cases is what you're after, in addition to controlling the charge on those layers. So you get rid of, you get rid of the tilt because they stand upright, and you get rid of the gauche defects because they don't have any flexibility. They're rigid. And then on top of that, you can actually build extra interactions into them. So at low temperature, in fact, the dipoles line up nominally in violation of the Merman-Wagner effect, except dipole-dipole interactions are long range. And so that even happens across step edges. We can see like 30 or 40 structural domains get together into a single dipole domain. And so there are all kinds of ways to use those to advantage with further control. And as I said, now the next step for us is to use them for spin control, but already for making a robust contact that can be applied by, vapor contact or solution. They seem very well behaved.
Okay. So we have tried, I mean, the question, just to give some background, like, so we have been trying to improve this gold addition for these metamaterials and nanophotonic structures.
Yes.
So there, like, I've used MPTMS and other thiol bonds, right? So tried with the temperature dependent and assuming that this dipole orientation will matter, but the low temperatures were even worse. Like, so we had these big clusters which are forming.
But these will be robust down to low temperature. They're actually more robust at increased processing temperatures than the alkane thiols are.
Yeah, thank you. So there's one more question or query from on the chat from Dr. Bipin Kumar. So he's asking like what will be next generation beyond 0D, 1D, 2D, and 3D? Can you put some light?
Yeah, I don't think we're done with those yet.
Right, quite a.
I mean, there's a lot we can do in terms of, precise materials. So, think about even as we make semiconductor devices smaller, the statistics of the dopants become problematic. If you have 0, 1, or 2 dopants in a very small volume, those are different materials. Whereas if you made an atomically precise structure, you could have the same every time. Think of those tiles I showed on the last slide. Those would have precisely 1 dopant each. And so you even control the exact position of it. So I think, from someone who likes everything just so, my ideal materials would be every atom is right where it's supposed to be. And what that means is you get over some of the problems with, statistically varying materials. Now, do I know how to build out in 3D? No, but I'm getting to the point where I know how to build in 2D. So, that's a start. And people who really know more chemistry than me, hopefully in the audience there, can figure out how to do that in other dimensions.
Thank you.
Okay. Thank you both of you. It's a very highly informative interaction. And thank you, ladies and gentlemen, for your time and patience. We are extremely privileged to have you all here today. I would like to thank our guest for giving his valuable time to sparkle our event. The inaugural session is over now, and we are moving for our next session. That is the first plenary session of the conference. We have some time for that. So if anyone wants to ask any questions or any interactions, please continue.
I'm audible? Hello, I am audible?
Yes.
Professor, I want to know if you see the scenario of the evolution of the material. So people evaluated the first discovery like 0D, 1D, then 0D. Why 2D is so much late?
Why is it so late?
Yeah.
Yeah, that's an interesting question, right? Graphene could have been produced as soon as we had Scotch tape, right? Effectively, right? And even in the graphene flagship and in the Singapore one now, they make pencils out of different 2D materials in order to draw those 2D materials like the transition metal chalcogenides. I think some very smart people were thinking earlier, Millie Dresselhaus in her head had graphene decades earlier. And not enough people paid attention to her to think how valuable it would be to have such a material separated on its own. But I think, one of the real strengths of Kostya Novoselov was to know what to do as soon, and Geim too, of course, right? But to know what to do as soon as he had the material. That was, moving at incredible pace through the science and demonstrations, and their scholarship was really extraordinary once they had that material in hand. But you're absolutely right. There's no reason it took so long to make it. It could have been done many, many years ago. And, in fact, in some ways it probably had been, right? The way we always clean 2D materials was to cleave them with Scotch tape. So sometimes we were probably making 1D materials, but we're throwing them away because we're looking at the surface, the fresh surface of the cleaved material. Kind of embarrassing in retrospect.
Actually, I'd like to discuss like the Velas in 1937, they just to propose like this theory of the 2D cannot be adjusted. So because there is some limit, like the block, if you depth in the block theorems, right? So if you confine one direction, then there is a limit to to realization for the crystal structure. So actually, I mean there is some light to put in that direction, like how that limit is going to break, and ultimately people realize that no, it is possible.
Right. That's right. And lots of the things that we thought were real rules in 2 dimension don't always hold up. I mean, we still have Peierls distortions in one dimensions and so forth, but like just exactly the, Merman-Wagner theorem about how you can't have a, 2D alignment, just you get over that as soon as you add something more than two body interaction. So, a lot of those rules turn out to be not such strong rules.
So the last
And
one,
it's interesting to figure out what their limit. It's interesting to figure out what their limits are.
I have a great opportunity to interact with you, so I will ask you one more question.
Sure.
Recently, I just to listen about the building block materials. That is the totally different from the 0D, 1D, 2D, and 3D. If you
Right.
light, that will be great.
Yeah, I agree. Yeah, there are huge opportunities there particularly for people to get together across different fields. And these, I think, one of the most interesting fields right now is the precise polymer. And so, we know there's like a lot of things, there's an existence proof in nature, right? We know how to program DNA to make a precise polymer, and that lets us make RNA, and that lets us make the primary sequences in proteins, but we haven't yet developed all those skills in synthetic polymers. And there can be very big opportunities for people who are, associated with the theme of the meeting in doing that.
Thank you. Thank you.
Yeah.
There is some technical issue for Dr. Chetna and Dr. Bhunesh Gupta, so he must be joining very soon. So you can continue your discussion for the meanwhile, sir, if you have any kind of questions.
If no one, then again, I will ask you one more.
Sure.
CNT discovered many years ago, right? And people know the unzipping of the CNT, in that time even. So why the ribbon-like structure emphasizes more? Even the aspect ratio of the CNT is same as what you are trying to show in the graphene ribbon. So only the reason behind the distribution of the arm chair, that is you can say the dangling bonds is going to change the angle, and the surface energy is going to change in both cases, totally different, or other reasons for that to again this kind of the ribbon is going to explore.
I missed the question there somehow. I'm sorry.
Okay.
Tell me
I'm
one more time.
trying to again to repeat my question. Suppose we talk about the CNT, parallelly
Yeah.
talk about the ribbon, and
Yes.
CNT like single wall nanotube, and
Right.
ribbon is like the unzipped ribbon, right? So only
Yeah.
the difference is the dangling bonds, the
Right.
curvature,
Satisfied. Yeah.
right? So there is only the reason to explore the edge dangling bond and the surface dangling bond to use the ribbon as compared to
Okay.
the nanotube.
Oh, yeah. So, I mean, for me, the opportunity is I know the chemistry of those edges and I know how to build it out into the contacts. Carbon nanotubes is a little more complicated in that it's not all exposed to me. There are sort of two layers I have to look through, and I don't necessarily know when there are defects, for instance, or the most likely ability to attach would be at the ends, which tend to be kind of messy.
Okay.
And so people like, Jim Tour have sliced open a carbon nanotube to make a graphene nanoribbon. That's one approach, but that's not exactly what you're looking for, I think. I think it may be easier to preserve the conjugation in the graphene nanoribbons ultimately. And when you have the carbon nanotubes, if you try and bring them close together, you can get, distortion and crosstalk. So we focus more on the systems where we can, spread them out and then figure out what their properties are and how to modify them. Partly it was just we knew how to do some of that surface chemistry already.
Any effect of the surface ratio? I mean the aspect ratio. Suppose we are taking the nano ribbon or the square sheet. So there is any scientific reason to take the ribbon?
Well, you can do what Nacho Pascal did, is just make them all the same because they only have one way to grow. That is one opportunity.
Okay.
Yeah.
I think Dr. Bipin okay, so he's through. So I think we can check on the YouTube channel if there are any questions, or if anyone else has a comment or question.
Yeah,
Sir,
one
there are many
question. Yeah,
questions on
yeah.
YouTube.
Am I audible?
Yes, please.
Yeah, actually, I'm sorry, I just got disconnected in the last slide. So you were talking about the perfect contacts. So I just want, my question is regarding that, what the perfect means what? Like, is for particular application you are talking about, and what is, I mean, the perfect contact is actually about?
Okay. So yeah, so in the sort of general term, it would be having a contact that's optimized for transmission. And
Okay.
so if it's just electronics, then you want perfect band alignment, because then you minimize the resistance. So your laptop, you could actually put in your lap without burning your lap.
Yeah.
Example, you use less battery and less power. In the case of spin, right? If I control the spin at an interface, and then I would have a simple, nanometer scale, room temperature way to do spin selectivity, I would have a number of ways to use that to advantage in quantum information and sensors and spintronics and so forth.
Okay, so you're talking about the spin matching, like for example, for LEDs and solar cells, we want a sort of band gap matching. So
one could do that. Yeah,
okay.
That's another place. In transition metal chalcogenides and other 2D materials, right? If I could make robust, precise contacts to them, then I could employ those in devices as well.
Okay, fine. Yeah. Thank you.
Sure.
Yeah.
For these structures, like, so when for spin-based structures, it's not just the spin, but also the transport also matters, right? Like designing is not simple or straightforward.
That's correct.
Isn't it a challenge?
Yes, but I'll start with getting the bands aligned and the control of the spin, and then we'll go from there. And part of the transmission and all is getting rid of all the nodes and understanding what the electronic structure is. And then one hopes by doing a series of measurements that you get a predictive understanding. And then you can say, well, here are the contacts we want. Now let's come up with the precursors that bring those together.
Thank you.
And
I think
someone asked, oh, sorry, go ahead.
No, please go ahead. I thought like it's a very long talk, and you already answered quite a few. Thought you must be tired, so I just wanted to give you a break.
Oh,
but please go ahead. Please go ahead.
I was just going to answer a question that appeared in the chat, which is, what are the key challenges in peptide-based self-sum monolayers other than dipole directionality and temperature? Yeah, so the peptides don't behave as well, right? I like personally, being a control freak, I like using nature for inspiration, but then putting together a system where I know every atom is. And so what I'd like to do in each case is figure out, okay, what synthetic system will give me the result of the biological system, but being able to go from, for instance, in the switches, from quantum mechanics to mechanical engineering and experiment theory and simulation. And so the peptides we've done some measurements with spin, for instance, in chiropeptide layers, but I'm more excited about the ones where I can really understand them and know where, the exact position and structure. I think we're getting close to your next talk.
Yes,
thank you, everyone.
Thank you.
We have our first plenary session. We are just about to start in some few minutes. Our session chairs are here and our speakers are also here. I welcome you. Ranjan, could we start?
Please proceed.
Yeah, okay. To chair this session, we have two eminent scientists, Professor G.G. Scherer and C. Ram Ramakrishna. I would like to request our honorary chair, Professor Bhuvnesh Gupta, President APA, to introduce the plenary chairs.
Thank you, Chetna. What a wonderful feeling when you introduce your boss who was 30 years back, leading the group where I was working with him, Dr. Scherer, very renowned scientist in the field of electrochemistry and electrochemical energy conversion. Very nice personality, gentle personality, very caring personality. That's why I had when I was working with him. So I really appreciate that Dr. Scherer accepted my invitation to be part of this plenary session and chair it. Dr. Scherer is well-known scientist from Switzerland. There are few important information which I have to tell about both Dr. Scherer as well as Professor Sriram. Normally, I feel that if people are popular, they really should not be given a large or huge introduction, but still for a young generation, it's very important that they should know who is the person sitting in front of them. So Dr. Scherer, he graduated from Technical University, Munich, that's in Germany,